Another important concept is the notion of how you can draw curves on topological spaces. This comes up in a lot of different contexts. And so to formalize it, you say that if you're given some topological space X, which I've sketched as a torus just for fun, a continuous map F from the unit interval to that space is called a path. So a path is sort of some parametrized function, right? Starts at t equals 0, ends at t equals 1, and the function values take points in the space that you're concerned with. For example, I could take this point to be my initial point, f0. So at time 0, I'm at that point on the torus. And at time 1, maybe I'm at this point on the torus. So these will form the endpoints of my path. And then as I go, I trace out some nice smooth path. I shouldn't say smooth, I should just say continuous. Since we're dealing with a continuous map, if I pick 2 points that are close together in time, I sort of think about the interval from 0 to 1 tracing out time, then yeah, they'll end up close together on the torus. And so it traces out a nice smooth path, maybe something like this, on the torus. So that's our path. We say it has endpoints f0 and f1. And if it turns out that the endpoints are the same, namely that f of 0 equals f of 1, then you instead call this thing a loop. And the reason you call it a loop is because, say this was f0 and f1, I might do something wacky, but as long as I come back to where I was, and I get a loop. So all loops are paths. Not all paths are loops. So let me just write this in for a definition. It's a loop. And you can do a lot of really important things with loops in topological spaces. You can define something called the fundamental group, which tells you, in some sense, how many holes you have in your space, based on what the loops look like and how you can deform them and whatnot. For example, this purple loop I sketched could be contracted to a single point, which is really nice. But if I drew a loop like this, so that's my f0 and f1, my starting point and my ending point, I can't contract that loop, right? The inside of the donut's hollow, so I can't contract it to a single point. And somehow that makes a difference and lets you detect holes in your space. Similarly, you could draw a big loop around like that, and you wouldn't be able to contract it. So connectedness leads us to this notion of path connectedness. So if you're able to get anywhere you want in a space via a path, then you say that space is path connected. Okay, so the torus I show above is path connected because, like with this red path here, any pair of points I pick, I can get from one to another in a continuous way. So path connected is a really nice property to have. All this is saying is that for any pair of points, you can find a path between them. Let's just write that down. That works for any 2 points. Great. So path connected is actually stronger than connected, meaning that any path connected space is connected. But weirdly, and this violates intuition pretty harshly, the converse is not true. Namely, there exist topological spaces that are connected, but not path connected. Meaning, okay, you can't split them into two pieces that form a like disjoint partition, but you can still get from anywhere in the space to anywhere else in the space via a path. Or rather, I think I said that backwards. Yeah, you're connected, so you're not split apart, but you can't get from one part of the space to another part of the space necessarily. The quintessential example here is the space T, which stands for topologist's sine curve. It's the curve you get from the function sine of 1 over x. And sometimes people define it on different subsets. Usually you think of it as a subset of the plane. Here I'm just looking at this chunk of the plane from 0 to 1. And of course you can't divide by 0. So what do you do when x equals 0? Well, you tack on the origin. So I put a little dot down here saying, okay, the origin is a point in my topological space, and everything else is just something that lies on this yellow curve. And of course, as x gets really close to 0, 1 over x goes to infinity, and the sine wave oscillates back and forth infinitely many times. Gets real, real ugly to look at. So this space ends up being connected in that I can't split it apart in any reasonable way, but it's not path connected. And the proof of that is fairly intensive, so I won't show the proof, but suffice it to say, you can't get from the origin to any other point in T in a continuous fashion. The reason, so like no path exists between those 2 points. The reason being, at least in an intuitive sense, since this is oscillating infinitely many times here, there's no way to latch on, right? How would you connect to that in an intelligent way? You can't really do it. You can't sit down and write a function that starts at the origin and then connects up and then manages to settle out and connect up to here. Weirdly, does not work. But that's just a hand-wavy argument. Feel free to look it up if you want. Something that's easier to prove is that the space of all continuous real-valued functions on the closed interval from 0 to 1 with a certain metric is path connected. So again, remind yourself that if you're given a metric, that metric automatically induces a topology. Topology generated by the open balls under that metric. And so the continuous functions are path connected. What do I even mean by that? I mean, if you give me, okay, so here's 0, here's 1. If you give me some function f, it's continuous on 0, 1, so I should have drawn it starting here, I suppose. 8, 1 does that. There's f. And let's draw G in purple. Say that's G. Then apparently I can find a path between these 2 functions. How might you do that? Well, the idea is to do it pointwise, to take a single value x and say, I can certainly get from f of x to g of x in a continuous way, and then do that for all points. So the function you can define, the path you can define, we'll call it h, I suppose. H mapping from 0, 1, because I want it to be a path, so this is sort of like time. Mapping into my space x. And you can define it pretty simply, actually. H of, let's say, t. So for a given time between 0 and 1, you output, let's do it like this. Let's say I want to start at f, so f is my like initial point, G is my ending point, then I could say T f of x plus 1 minus T times G of x. Okay, and really I'm being a little hand wavy. This is a function of both x and t, even though I just said it was a function of t. But anyhow, I mean, you could write this as, just in terms of functions, t times a function f plus 1 minus t times the function g, if you like it like that. And then what do you see? Well, you see two things. H of 0. I guess I'm going backwards. I'm going from G to F. F of 0 would be 0 times F plus 1 times G, so that's G. And H of 1 would be 1 times F plus 0 times G. So this is certainly a continuous function because F and G are continuous. And I'm just multiplying continuous functions by some number t or 1 minus t. And the sum of two continuous functions is continuous. So as a whole, H is a continuous map from the closed interval to the space of continuous functions, where I start at G and I end at F. And G and F were arbitrary. Right? No matter what functions I pick, I'm effectively tracing out a path from G to F. And so what's really happening here, let me erase the red I have. What's really happening is you're starting at G, and then you're gradually deforming it to look like F. So maybe this was like t equals a quarter. This was t equals a half. So by the point half your time has elapsed, you're like the average of the two functions. And then you start to get closer and closer to the function f. It's t equals 3/4. And then once t equals 1, you've hit f. Whereas when t was 0, you started at g. So it's a nice way to smooth or continuously move from one function to another. And since you can do that for any pair of functions, you say that this space is path connected, because this series of red functions defines a path from G to F. All right, that's it. Thanks for watching.